Hello, and welcome back to the Cave Escape podcast. I'm Caleb Groves.
And I'm Ashton Goolsby.
And today we want to talk about math. And
the horror.
Yes. Specifically, math and why it's actually cool.
Well,
but
kind of like some paradoxes or things that we come across as we study it, but we don't often stop and consider. Somebody had to come up with that.
Right.
And somebody had to find that at some point. So the fact that we can even study it has to do with somebody's just curiosity at some point.
Mm-hmm.
And
like discovering it, and they were discovering it in the real world.
Yeah.
Like math is more than just you do this process to these numbers on this piece of paper. Like it's not only in the abstract.
Yeah. So now like we do things like geometry. To me is the easiest one to get. We do it because it's in a curriculum and they tell us to do it now. But at some point it was put in the curriculum because it was seen as a worthwhile thing to do. And why was it seen as worthwhile? Because somebody had spent the time discovering it in creation and said, hey, this is actually really important in understanding how the world works.
Mm-hmm.
And then over time it became assigned because they were like, everybody needs to know this. Right. And now, especially I think in more contemporary education today, we just are like, I don't know, it's there. We just do it because the teacher said that I couldn't graduate unless I did Algebra 2.
Yeah.
So we've just kind of been talking about some stuff
mm-hmm.
that we both find interesting, that we just kind of wanted to have an excuse to talk about some more.
Yeah.
Just
and kind of, just show how math can be grounded in reality and why it's actually important. Because another thing, what I was just thinking as you were talking about geometry just there was, and like same, like people say this about algebra too, but I think the analogy is more clear with geometry that like I don't need to learn geometry because I'm not going to go build stuff.
Yeah.
Like why do I need to understand geometry? And it kind of just feels arbitrary. Like education system just decided that geometry is what we have to learn, so we have to learn it. But like I'm not going to use this for anything. But it was originally put in the curriculum like years and years and years, like hundreds of years ago, because education was to learn about the world and to understand the world that we live in and creation. And so geometry is a huge part of understanding how that works. Yeah. But I think that it makes sense to be confused about why geometry is in the current, like contemporary, like secular curriculum, because that curriculum is set up in more of a learn stuff to have a job. And like, if you're not going to use it for your job, what's the point in learning it?
Yeah.
Because it's more focused at getting a job rather than understanding the world.
Which is unfortunate.
Yes. Very.
So that's part of what like all of our conversation with classical.
There's the classical again.
Classical education was saying we want to try to get back to this view of education as informing us in reality. Because I was talking recently to my dad, and he was saying there's two kind of pitfalls you can fall into. You can fall into one where you study something because it's purely useful, but then we can also fall into another one on the other side where it's just we put the academics up on a pedestal and like, wow, look, they're so great, and just these fancy ideal things we can look at.
Right.
But I mean, there's this middle of the road kind of. It is beautiful because I mean God made it and it's ordered, and it's wonderful to look at this order that God's put in the world because we live in that order. But then there's also, I mean, it does have use at the same time. So we don't just study it in like, well, forget the use. There is use in it. There's practicality in it, but also we don't just want to take it and just, well, it's useful and we're going to take it and make things with it and disregard the beauty and the order of it. It's
right.
We want to study it because we can use it right now. You got to find like the middle of the road. It's useful, but it's beautiful.
Yeah.
So it's worth studying for itself to an extent.
Yeah.
But also it does have practical use too.
Yeah.
So,
like the beauty can be studied for its own sake, not for a utilitarian purpose.
Yeah, but at the same time, like there's that middle of the road where you have to acknowledge there is use in it.
Yeah.
But there's also beauty to be studied.
Mm-hmm.
So not falling on one side of just reveling in the beauty and forgetting that there is a practical reason for studying it, but also not going to the practical and forgetting that this is also something that is beautiful that we should also consider for its beauty as well.
Right. And I think
Sometimes
probably,
we tend to pick one side and go, "Oh,
Yeah.
it's useful," or
Yes.
"This is just beautiful." Forget the use. And
yeah,
it's a hybrid of both.
yeah. I feel like one of like the math things that it's actually easiest to see both sides of would be like the Fibonacci sequence and the golden ratio. Because I feel like it would be very difficult for anybody to look at that and be like, and not think, wow, how cool and beautiful is that occurs naturally, but also not look at it and go, look how useful this thing is.
Yeah.
Because it's used everywhere. Like, as humans, we've developed like I think I forget, like electrical systems based around it, and like other probably like computer things, I think, using it. I'm not actually sure about that. I was just reading about it earlier today. But there's like some crazy things that we've created with the Fibonacci sequence, and the golden ratio happens everywhere. Branches on trees
Yeah.
follow the Fibonacci sequence. Also, the Fibonacci sequence is different people start it in different places. Some people start 0-1, some people start 1-1, but basically
Usually
it's
zero. Or you're right.
Also, I mean, I'm of the opinion that 0 isn't a number, and it bugs me that we start the number line with 0 and consider it to be like a number, but that's a different conversation. But each, like, it's a sequence of numbers, and each number is the sum of the previous two numbers.
Yeah.
So you have like 0-1.
Yeah.
You add those together, you get 1. So then you have 2. You have 1-1. Those equal 2. Then you have 1 and 2. That's 3. 2 and 3 is 5. 5 and 3 is 8, and so on.
Yeah.
And so it kind of compounds exponentially, but like with each, like the ratio between each number is the same, I think, or something. I forget how the Fibonacci sequence is related to the golden ratio, because they're like the same thing.
So it's like you were saying, the two numbers equal the one that they're followed by. So you start with 0 and 1. 0 plus 1 is 1. So the next number in the sequence is 1. Then you leave the 0 off and you just add the two ones. Well, of course, you get 2. Then you add the 1 plus the 2, you get 3. Then you add the 2 and the 3, you get 5, and so on. What it is there's and there's things you can do with that sequence themselves, but also there's a ratio in there of if I divide the two numbers next to each other, I'm ultimately getting closer and closer and closer to this irrational relation or proportion that can be found in nature. And so what I was looking at earlier when I was looking at stuff about the Fibonacci, it doesn't actually attest a person to discovering it. We name it after the person who officially wrote it down. But they said India, they had records of hundreds of years before that using the Fibonacci sequence. They had discovered it.
Oh, yeah.
But eventually I think it was a Greek guy, wrote it down. And
Interesting.
what it is, though, is they found there's this pleasing relationship of the proportions of shapes of things, and it's certain things in nature just grow in this height to width ratio. The most common example people give when looking at the Fibonacci sequence or the golden ratio is the spiral on a snail shell.
Yep.
So what you would do is you would draw a box. You would start with the 1 to 1 because obviously you can't draw something that's 0. So you would draw a box it's a square 1 by 1. Then off of one of those sides you would extend it out to be 2, and you would complete a rectangle off of it. It's confusing to talk about without actually drawing it out. But on top of this 1-to-1 square, you would construct a 1-to-2 rectangle. Mm-hmm. Then on top of that 1-to-2 rectangle you've made, going off a different direction, you would do a 2-to-3. So you create this like kind of twisting, and you can Google it and find people that have drawn it.
Yeah.
But if you look, they start with these little bitty boxes, and they get bigger and bigger and bigger, and they kind of twist around each other. If you join the adjacent corners of all of those little squares and rectangles, you get this growing spiral out.
Yeah.
And if you were to look at a snail shell, that is actually the same proportion out from the center of a snail shell.
Yeah.
And so there's plenty of other things that if you look in nature, it pops up there.
Mm-hmm.
But it's also just like, even in things that we make, as we make certain things, that's the proportion that we follow because it looks the most pleasing, and we don't even think about it. Like if you pull a credit card out of your wallet, credit cards are generally, I think they're all the same size, made according to the golden ratio.
That's cool.
And if you look at, this used to be true, at least I know. I can't remember which generation of iPhone it was specifically, but we compared. My brother had an Android phone, and I always thought it looked really like long and skinny,
Mm-hmm.
and I couldn't figure out what exactly was wrong with it. One day it hit me. I thought, I bet my iPhone is in the golden ratio and his isn't. And I checked, and the iPhone was pretty close to it. I think it was actually, it may have been the
That's super
I
interesting.
think I have a 12. I think it was this one.
Interesting.
But I was like, the screen of mine, not necessarily the phone itself, the screen was pretty close to the golden ratio. But then when I looked at his phone, it was much longer than like the width of it. And there was something about it. I was like, mine, I feel like is just aesthetically pleasing to look at.
Yeah.
And to like watch videos on or whatever. Versus his always, it bugged me if he showed me something on it because I was like, it looks squished.
Interesting. That's cool.
I was like, that's weird. But we do a lot of the things we make. If you look at it, it's just a thing that's been ingrained in design.
Yeah. And also like paintings and photography.
Yeah.
Like it's huge in those things, and like the placement. Like if you're painting, like artists who paint stuff, they use the golden ratio. The golden spiral is like the spiral shape that's made with the golden ratio.
Yeah.
To place things in certain areas.
Yeah, so it's like a cool little puzzle because you can look at artwork. I saw one recently that was diagrammed out where you could see the painting was actually following the golden spiral based off of the placement of things. It all fit perfectly on the golden spiral.
Wow.
It was pretty cool.
Yeah.
So it's one of those cool, everybody knows this, everybody's working it in there. And so you can kind of look for it and find it as like a little thing to look for in pictures
Right.
when people paint them or draw them.
But it's also more than just a fun
yeah.
Easter egg that people are sticking in their paintings.
Yes, they're putting it in there because it's a thing that's found in nature and it's pleasing to look at.
Yeah.
But also they're putting it in there and everybody can go, oh, look, the golden ratio's in there if they're educated and they know what they're looking at. But they're doing it because it's a practical thing to do. It makes the painting look nice, but also it's a natural thing that they've studied as well.
Yeah.
So it's kind of that hybrid of the two. It's a practical thing, but also it is a beautiful thing.
Right.
They can use it in the picture, but also it creates a more beautiful picture when they do it.
Mm-hmm. Yeah.
So it's more than just a string of numbers.
Right. Yeah, that's true.
Which was funny because my dad made us memorize it when we were little, and I was like, I don't understand what this is. But after studying it more and looking at like art or literature, or I think somehow it works into the Divine Comedy. Somebody pointed out at one point. I don't remember that one. That'd be worth looking up if you want to look that up.
Yeah, I bet it's definitely in there.
But it's all throughout like art and literature, and beyond that, those are human-made things. But then it's derived from just the way the natural world works. Like there's some, like you were saying, like trees and things you can look at.
Yeah. Like I forget how, like I don't know all the things that it is, but it shows up literally like all over the place in nature.
Yeah.
It's like so many things just follow that pattern.
Yeah. And so like I said, it's the ratio of the two numbers next to each other. You divide the big one, I think it is, by the small one, and you get closer and closer and closer to this ratio. So if I started off with what, 1 to 2, so like in the sequence, we have 1 and 2 are next to each other. So I could do the 1 to 2, which is close to the ratio. If I then move, the next one to be 2 and 3. If I put 2 and 3 in ratio, that's closer to the golden ratio than the 1 and the 2. The next would be 3 and 5. That's even a step closer than the 2 to 3. But it's an irrational ratio. The bigger the numbers get, and we put them in proportion to each other, the closer we're getting to the actual golden ratio. But it's irrational.
But what is the actual golden ratio?
The actual golden ratio, it's irrational. We can't actually write it out.
But you can get, because like even pi is a fraction.
I don't know what it actually is. I mean, I could Google it real quick or something. But but with the sequence, what it is you're eternally getting closer and closer and closer to the actual ratio. The further down this extending string of numbers you go, the closer you get just ever so minutely to this irrational number.
That's interesting. So, according to Wikipedia, the golden ratio is equal to the ratio of the sum of two adjacent numbers to the larger of the two numbers.
Yeah. So like if you
add the two numbers together, that number in ratio with the larger of the two numbers is what the golden ratio is.
Yes, I saw that as well. That you can look it up. It is on Wikipedia. They have a diagram drawn on there. I saw earlier.
Mm-hmm.
So it's a line. You've got an A section and a B section. So it's basically saying if we took a number A and a number B, and they were in this proportion, we add them together, the sum of their whole would be.
It'd be like A plus B over A.
If this makes any sense to you,
yeah.
It'd probably
if you can visualize
if
math.
if you looked up the golden ratio on Wikipedia, they have a picture there that it's much clearer when you see it written out. I tried to read their little article before I looked at the picture, and it made no sense to me. But I looked at the picture and it's like, oh, this makes sense.
Yeah.
But it's the relationship of these numbers. But if you think about it, A plus B, the sum of those two, the relationship of the sum to A is the same as A to B. That's still just the Fibonacci sequence, because if you have A is 3 and B is 2, their sum is 5. But then you have, that 5 would be the next number of this Fibonacci sequence. So then you could just do, now 3 has become B and 5 is A. You add them together, you get 8, which is the next number of the Fibonacci sequence, which of course is in the same ratio. 8 to 5 is 3 to 2 because they're the same sequence.
Right.
So, I mean, it's just working that out geometrically, which is the cool thing that I didn't know until doing arithmetic with Mr. Spun. The hardest part is a lot of the arithmetic was originally worked out a lot of times in a geometrical way.
Right. Like
So
most math
Yeah.
can be geometry.
Yeah, which was crazy because you can use lines to represent numbers.
Yeah.
It's like you pick a line and you say this length right here equals 1. This is what we're counting with, is this short little stick here. And then you measure everything else with this stick and you say this thing is 5 of these little 1 sticks long. So we're going to say that's a 5 and this is a 1. And now we're going to examine the relationship of this stick here versus the big 5 stick.
Yeah.
Versus a 18 stick. And that's so they would draw it out, and it's crazy because it's one of those, we just do it now with Arabic numerals, and we like do it on paper, do it in your head. Or with a calculator.
That makes so much sense.
But then we would the Greeks would draw it out with shapes and lines.
And they'd be seeing actual ratios of actual lengths of lines, not just, well, this little squiggly line right here represents 3. Because that's really what it is. Like, our Arabic numerals represent actual realities. Like, if I see a group of 3 things, that's more actually 3 than our Arabic numeral for 3.
Yeah. Which was actually, when we had Mr. Wilbur on, I think it was in episode 3, he was talking about we should try to emphasize with younger kids, like counting with like pips or something, instead of just saying 2 plus 2 equals 4. This squiggle plus this squiggle equals this squiggle.
Right.
Making sure that they have the concrete. I have 2-ness and then I have another 2-ness. And you can see 2 and you can see 2. But when I put them together, I don't have 2 and 2 anymore. I have something different.
Yeah.
But I still have 2 and 2.
Yeah.
In fact, I also have 1 and 1 and 1 and 1.
Right.
But learning to see it's more than just this squiggle plus this squiggle equals another squiggle. Because, I mean, the Arabic numerals are good for mercantilism. It's good for adding and subtracting, dividing and multiplying quickly.
Yeah, so you don't have to, like, write 25 dots.
But, like, Roman numerals, you're seeing that when you look at it. So Roman numeral 1 is a line. Roman numeral 2 is 2 lines. 3 is 3 lines. 4 is 1 line less than the 5. So 5 is its own thing, but 4 is shown in relationship to 5.
Yeah.
Just like 6 is shown to be
so it's kind of in between.
Yeah.
Because it's kind of, they still have like representative symbols.
Yeah.
But you're also still actually just like adding the things together.
Yeah.
That makes sense. That's cool. So that actually makes a lot of sense of why that's how people think of math now. Like you were saying earlier today, of it being like this abstract thing that's just like you're just You just have to learn how the process goes, and then you just apply the process to these symbols on the paper.
Yeah.
And then if you do the process correctly, then you end up with the right symbols at the end.
Because we're a highly industrial society now.
Right. But yeah. And so if it's because the symbols that we're using are like abstracted from the realities that they represent.
Yeah.
And then we've kind of divorced them from those realities, and we just deal with the symbols without talking about what the symbols are pointing to. That's super interesting.
Yeah. And I guess it can sound like we're like condemning, like we should just go back to Roman numerals. I mean, Arabic numerals are very helpful.
Oh, yeah.
They're very helpful, but there's also, I mean, either
but
way.
Like what I was just saying.
Yeah.
We need to, symbols are great. Words are symbols. But we need to, it's very important to understand what the symbols are pointing to actually understand like what the symbols mean and what they're for.
Yeah.
Because if you're just dealing with the symbols devoid of what they're pointing to, then you're not going to understand what they're there for. That's why everybody hates math, because they don't understand it, because they don't know what the symbols are pointing to.
Yeah. So the struggle that we have because we use Arabic numerals is getting back at the more concrete. Well, what does this actually do?
Yeah.
What are we saying when we say 2 + 2 is 4?
Yes.
We think, oh, it's just common sense. Everybody knows 2 + 2 = 4. And at some point, I think, kind of get to that idea. But
yeah,
it kind of is something that I feel like younger kids get frustrated with because a lot of them aren't as good at abstracting it out.
You're right.
That's been a struggle I've had teaching 4th graders, is some of them can look at it and abstract it out, and they can get it quick. And there's some who don't. They just look at it and go, I need you to give me the process because I can't conceive of this in the abstract. So
yeah,
that's been kind of a challenge. But it's fun.
Yeah.
It's fun to try to help them see it a different way. But so there's plenty of places that math is. I'm trying to think of the word I was going to use. It just escaped me. Like math is, again, it's something that's in reality, and somebody had to conceive of a question at some point, and then leading down these rabbit trails of some question that popped in their head, they discovered things like the irrational number pi, or like square root of 2. You can draw out square root of 2 like through a geometric process, and you can look at this line and say this equals square root of 2. But you can never write out the square root of 2 as a numeral. It's irrational. But you can draw like a triangle on a curve and like a square and go this line right here and this line right here equal these numbers, and then this right here would be the square root. This line would equal the square root of 2 in relation to that line there.
Yeah.
If that line was 1, this line would be the square root of 2. That's the exact length of it. You can't measure it. You can't like tell what the length of it actually is.
Because if you wrote it out, it would just be an
ridiculous.
infinite decimal number.
Yeah, so like we can build buildings and be like, this line is the square root of 2.
Yep.
And we can geometrically work out and create, okay, here is a line and here's a stick that is square root of 2 in length. But we can't actually like write down what the square root of 2 is. It's crazy.
Yeah. And there's a lot of numbers like that.
Yeah. But then there's even like beyond that, like you start getting into other crazy paradoxes even. So square root of 2 was banned from talking about at one point by the Greeks because they worship numbers, and they said this kind of puts a hole in our religion of numbers. We can't explain this number. Don't talk about it. And then eventually they got out. But then, I mean, that's one we can kind of conceive of. But then there's even other bigger paradoxes that even still today we can kind of look at them, but they just blow my mind.
Or like Zeno's paradox.
Which one's that?
Zeno's paradox is the one where like you can never actually, like I can never actually reach that wall if I walk half the distance to the wall, and then I walk half the distance again.
Oh yeah.
And then I walk half the distance again, and I'm just gonna walk half the distance forever for infinity because there's always gonna be another half to walk. And
you
so
can always divide
I'll
something
never
in half.
I'll never actually touch the wall.
I forgot about that one. I hate that one.
Yeah.
That one hurts my head. But then there's also, you got onto me. I was listening back to one of our other episodes, I think to put a blog post or something. You called me out for talking about greater or lesser infinities. But that was one thing we talked about was infinity.
Yeah.
That paradox. Do you want
Yes. Yeah. So it's not as much of a paradox as much as it is our finite brains can't understand infinity. But so I really like it because I really love brain teasers, and I love things that like stretch my brain farther than it can actually go.
I like it too. It really hurts my head.
Yeah. So, okay, wait. What's the best way to explain this? Okay, so if you have a set of numbers, so the set of all even numbers is an infinite set.
Uh-huh.
Right? So you've got, because there's an infinite number of even numbers. And in set theory, you can say that one set is equal to another set by, you can either like count them and be like, well, there's 10 things in this set and there's 10 things in this set, so they're equal. But you can also just do it by lining them up. And you have like a 1-to-1 correlation between everything in both sets. And so you know that they're equal without having to count them. And people used to do that all the time too. I was watching this video and he was talking about how like shepherds would just like drop little stones as their sheep went through the gate. And then when their sheep came back through the gate, they would just pick up the stones to see if they had the same number of sheep without having to actually count the sheep. And so you just kind of like do this correlation thing. And so if you take the set of all even numbers, which is an infinite set, you can line it up with the set of all whole numbers. And basically go, okay, so you have two...
All whole numbers or odd numbers?
All whole numbers. So even and odd numbers. Because you can line up, you can basically just number the even number set.
Oh.
So you can line up 1 with 2, 2 with 4, 3 with 6.
So like you're counting, you can count all the even numbers by whole numbers.
Yes.
So like let's look up. I have a list of like 2, 4, 6, 8, 10. How many even numbers do I have? I have 2. Okay, 1, 4, 2. Okay, you can count
3,
them
4,
out
5.
and go, okay,
Yeah.
I've got 5 even numbers here.
Yeah.
But you've just counted numbers with numbers.
Yes.
That's crazy.
So you can do that for infinity. And so the set of all even numbers, which is an infinite set, is equal to the set of all whole numbers, which is because it's also an infinite set, even though that's even and odd numbers.
That's crazy. I forgot about that.
Yeah. So it's super weird.
I'm sure we went over that, but oh man, that makes
And
my head hurt.
Yeah. So that's countable infinity. Means that you can count it. If that way.
Itself doesn't make sense. Countable infinity?
Yeah. It just means that you can actually count it for infinity, and like theoretically, if you could make it an infinite list, then you could list all the things. But irrational numbers. So the weird thing with irrational numbers is there are more irrational numbers in the set of all irrational numbers than there are whole numbers in the set of all whole numbers.
You're gonna have to explain.
Yeah, I'm gonna explain it now, and this is gonna be really tricky without being able to like actually demonstrate it, because it's kind of like it's more. I know how to explain it visually better, but basically, say you have a set, you just have like this giant list of irrational numbers, which are infinite decimal numbers, right? If I take the first number of your first irrational, if it's a 1, I make it a 2. If it's not a 1, I make it a 1, and I write my own. I'm making my own number, because what I'm going to do is I'm going to write a number that's not on your list. So if the first number is a 1, I make it a 2. If it's not a 1, then I make it a 1. So I end up writing this giant number that's just all 1s and 2s. And what happens is that number won't be on your list, because even if you have, because like if you add that number to your list, let's say that's like, let's just for the sake of simplicity, you have 5 things on the list. If that's the 5th thing on the list, when I get to the 5th digit on there, if it's a 1, I'm going to make it a 2, and if it's not a 1, I'm going to make it a 1. And so now the 5th digit is different on this new number that I'm making. Does that make sense?
Roughly. I remember talking about this one, and it did at one point. Where were you reading on this? Because you were reading on this earlier today.
I watched like a TED Ed talk thing.
And what's it called again?
I don't know. I mean, it's not really like a thing that's called that. It's just this. I'm describing the proof for irrational numbers being a greater infinity.
I want to go back and watch it later. You have to show me that video.
Okay, yeah,
later.
I will. Basically, how it works is if you do that process, then you're going to end up with a number that's not on the list of infinite numbers. And you can do that infinitely.
That's crazy.
So there's always going to be numbers, there's always going to be irrational numbers that are not on your imaginary infinite list of irrational numbers.
Math was not my best subject in school, so I can appreciate it, and sometimes I can get it. And there's sometimes like this where I almost get it, and I can't figure out where I'm not getting it.
Yeah. I mean, that one's really, yeah, I get. Like, it stretches my brain beyond what I actually, because we can't understand infinity.
That's true.
So, but that's kind of, you just kind of got to trust that that's how that works if you don't want to try and figure it out.
So, like, testing infinity is basically just, it's kind of like, excluding recent discovery, like, we had a model of the atom before we'd ever actually seen the atom until recently. We had never seen the atom.
Right.
We had a model that's based off of, like, things around it and rules we could kind of put in place about other things that led us to this idea of,
Right.
hey, this must be here. What can we say about it? And we could start naming properties of it before we'd actually seen it. Which is kind of like what I was saying with like the idea of infinity. It's like even with like imaginary numbers. They were invented at some point because somebody had a question about something that they started pursuing it and trying to figure it out, and they had to discover this relationship, and they had to explain something somehow, and they made up a way to explain it. But then we started delving into imaginary numbers, which led us to other realizations of other relationships of other things. And then like these ideas about infinity, it's like somebody just sat and had a question about one thing, and they kind of started plugging away at relationships of things, and eventually said, well, I guess we logically would have to say this about infinity.
Right.
And it's cool, but it hurts my head.
Yeah. Or like there's like the thought experiment of the infinite hotel.
That's probably the one I can get the best.
Yeah. And so it's like if it's all full, all the rooms are taken, and a dude comes in and he's like, hey, I need a room. Then the clerk guy, like, what's he going to do for this guy to get a room? What he does is he just asks all of the people to move up one room. So the person in room 1 moves to room 2, person in room 2 moves to room 3. And so then everybody just moves up a room. There's an infinite number of rooms, so they can do that. And then room 1 is open. So then he just does that.
Yeah.
But then if you have like an infinite bus come in with an infinite number of people in it, I forget. Hang on, let me look at my notes really quick.
Yeah, that was the one where it hurts my head.
This one actually isn't super complicated.
And
everybody moves.
Did you mention that like it's a hotel with infinite floors, infinite rooms on each floor, and they're all full?
Infinite number of rooms only.
Oh, so infinite number of rooms.
Because if you did, infinite number of floors with infinite rooms on each floor would be a lot more complicated.
Yeah. So just infinite rooms, and they're all full.
Yeah. Also, this was invented by David Hilbert in the 1920s. But for the infinite bus, then he moves all of the tenants. He has them take their room number and multiply it by 2 and move to that room. So then he moves everybody out of the odd rooms into the even rooms.
Yeah.
And so then all of the odd rooms are empty, and there's an infinite amount of odd numbers. So then all of the people in this infinite bus can just fill up all of the infinite odd rooms. And then it goes into like, what if there was an infinite number of infinite buses? And like, how does that work? And it has to do with prime numbers and stuff. And that one's a little bit more complicated, and I don't think we have time to get into that.
Yeah.
But basically, it's like,
I don't think I could understand it anyway. I can get up to the infinite buses one, and then I think we tried to do that one, and I was just like, Mr.
that one's a lot harder to do, I think, without some kind of visual aid.
Yeah, a lot of these, the best, like I was even saying with like the square root of 2, a lot of this you have to see some type of representation drawn out somewhere. Because just to talk about it, it's too much to keep in your head.
Yeah, because it is irrational.
Yeah, if you can try to visualize it, which usually ends up being an analogy of some kind. If you can visualize it some way as well as try to think of it in your head, then you can usually get it.
Yeah.
But it's just crazy. But like we think of like math as like 2 + 2 = 4, or like I'm working at Chick-fil-A over the summer. I had a lady come through earlier today, and she paid me with a 20, and her total was like $17.53. And I just looked at it and said, okay. And I just counted out her change before I even put it in the machine. I just clicked it out, handed it to her, and then I did the actual input when she was gone. So we think of math as like that kind of stuff.
Yeah.
If you want to be an architect, then study this type of math. If you want to be a rocket scientist, study this kind of math. If you want to be an accountant, study this math. And if you want to be, I don't know, a musician, study this kind of math. I was thinking like if you're going to be like a welder, then, well, you don't have to study math because you'll never use math in your daily life. would be the idea.
Right. Yeah.
But
But actually, it's not just like, there are technically different kinds of math, but they all have a commonality in that they're like a part of like God's creation.
Yeah.
Like they all occur naturally, and we've just discovered these patterns that God put into the world.
Yeah, and you encounter them daily.
Yeah.
So everywhere you go, you're encountering math on some level.
Mm-hmm.
And
motion.
Yeah.
Is
that's
math.
crazy. Yeah. But that's really like, this wasn't even something we planned about talking about, but that's why the quadrivium is divided up the way it is. It's a study of math because they realized, I said, everything that we encounter can pretty much be explained in the physical world.
Yeah.
World can be explained mathematically somehow.
Yeah. Galileo, math is the language of creation.
Yeah. So, I mean, studying math, it's more than just 2 + 2 = 4. You're studying almost literally everything in the physical world that you interact with. You can understand with math somehow.
Yeah.
So you've got like the trivium of the language of like how we speak to each other, and the arithmetic or the quadrivium is the language of the cosmos, which is math. You're studying math.
Mm-hmm.
I just made that connection in my brain back to the other stuff. But
yeah,
like that's
that is
why
really cool.
That's why to me this is so cool. Because I mean, whether you're going to be an accountant or whatever, you're encountering math every single day. And so studying math better, and I would say this to somebody who was horrible at math in school.
Yeah.
I was not good at math. The one class that I consistently got bad grades in. But like you study it, and I mean, it really opens your eyes just to see how wonderful creation is.
Once you understand it, though.
Yeah.
Once you understand that these are symbols pointing to things that are like a part of the order and patterns that God put into creation.
Yeah.
Because if you miss that part, then you miss why it's beautiful and why it matters.
Yeah.
So,
I don't know. I've gained an appreciation for math over the past few years.
Yeah, that's awesome.
And I've wished that I had a better teacher in high school other than myself.
Right, yeah.
I was mostly self-taught due to homeschooling.
Yep. Yeah. Alrighty, well, we're a little bit over time, I think, today. But that's okay. Thank you for listening.
Stuff will be up on the blog. It's the Cave Escape
.blogspot.com.
I can never remember the URL.
That's so weird.
And I'm the one who's in charge of the blog, and he's the one that remembers.
I've been on our blog like twice probably.
We updated it recently, so it doesn't look like garbage anymore.
It does not look like trash.
Yeah, hopefully it looks somewhat decent and respectable now.
I think it looks pretty respectable.
Oh, thank you. Because I did the update.
Yes, you did. You did a very good job.
But you can also email us at greatcavescape@gmail.com. If you have any questions or feedback or anything, we welcome it. We've gotten some recently, and it's been really helpful. Some critiques of things that we said that we could have said better, or things to go look at. Mm-hmm. If you have anything, feel free to comment on YouTube or Spotify. I think Spotify has something. Or you can just email us there if you have something, or Facebook or Instagram.
Yep.
We're on those. So thanks for the people who've sent us stuff so far. It's been really helpful.
Mm-hmm. Yeah. All right, well, thank you for listening this week. And until next week, take care.